Yo, yo, yo. What's up? What's up? Welcome back. Today we're working on my operating system. It's called StreamOS. It's a toy OS written for fun, by some metric of fun. And we have this like kernel right now. It like boots in QEMU. Just give me a sec. So this is a virtual machine. It starts up, it like draws something to the screen, and you can like play this little breaker game with WSD. And there's actually like a lot that has to go on to get to this point. It like has like some like boot stuff, memory allocation. It's got some like concurrency because at the same time we're also running this web server. Right, I can go here and I say like hello stream. And if I submit this, like it proves that it like got a request. Great. It's got like logging infrastructure. It's got like an Ethernet stack, which involves like PCI. And it's like some like network protocols, ARP, UDP, TCP, HTTP, all that stuff. It's got a clock so that it can do like sleeps and stuff. And it's got like graphics, keyboard, and multi-core support. So if I like refresh this, we can see that like this is getting dispatched to multiple like different CPUs depending on like what's available at the time. Wonderful. And so what we want to work on today, and what we've been working on for the past few streams, is USB support. So, where are we? We've been working on implementing UHCI support, which is like kind of the host side, like a specification for how a computer will talk to a USB device. So, sorry, a USB host device. Let's make that clear. So like, this is me. I'm the CPU. Hello. He's got like a little smiley face. Maybe he looks a little angry because the U looks like a V. And he has like a PCI bus. I'll draw a little bus here. Meep meep. Come on, the magic school bus. Right? And on this piece, this is like a PCI bus. And on here we have like a USB controller. So we'll draw like a little like PCI card. I think they look like this, if I remember correctly. USB. This is also connected to like memory lines. So kind of like this. I guess it's kind of more like this. So we can like talk to this USB through the PCI bus, or sorry, this USB controller through the PCI bus, or we can talk to it directly. And so what we do is we like query PCI. We say, hey, walk my PCI devices, and I like find this USB card, and then I go like, hey, where are like the memory mapped registers to talk to this guy? Like, how do I talk to this guy directly? And it tells me. And then this guy has like a USB port sitting on the back of him, right? And he maybe goes over to like your little mouse. Right. And so what we have right now is we're working on like this connection here. And we are implementing something called like UHCI. So the idea is that like many vendors could like make a USB card, and you would only need one driver to talk to all of them because they all implement the same like interface like here. And all devices implement like an API here. So really, like, you could like swap this out for any card. And in reality, there are multiple different kinds of cards here. There's like UHCI cards, OHCI cards, where this is like unified host controller interface, open host controller interface, I think, and then like EHCI for USB 2.0, which is like extended, and XHCI for USB 3.0. Anyways, the point is, we're kind of like implementing like a small subset of all of USB right now. And where we got to last stream was we had we like read this book. Sorry, I shouldn't say we. I before stream read like pieces of this book called like USB, the Universal Serial Bus, which kind of cleared up a lot. Book, and we'll look it up on Google, or else I won't be able to find it. This guy here, by Benjamin David Lunt. And this book cleared up a lot. And so we've implemented like kind of up to the point where this book like described to me like all the data structures and how to like prep the card and stuff. So we've kind of got to the point where we like understand it, and we've set up some like data structures for how to work with this guy. So specifically on like UHCI cards, the idea is you like initialize the card into like a certain state, and then basically all you do is point it at this like queue, this like list of buffers. You say, hey, here is where the list starts, and here's where the list ends, kind of. You say like how long it is, I think, or maybe it assumes it's 1024. And you have like elements in here. And what it does is the card says, I will basically service each one of these buffers at like a fixed interval. And so what you do is each of these buffers will like point to a like queue. They might point to multiple queues. There's like reasons why you would want to say point to multiple queues, but for now we'll say every single one of these will point to this queue of things to do. And in here, we just start, like all we have to do is start like appending requests. And so last stream, what we did is we kind of allocated this guy, we allocated these queues, as well as the like, they call them transfer descriptors, I think. I keep getting it wrong. Transfer descriptors or transaction descriptors. And these are like a unit of work, essentially. These are like, hey, do this thing. And we've got like these guys ready to go. And so now what we have to do is we have to actually start populating these descriptors with USB stuff in order to try to pull a USB mouse or something. So that's what we're working on today. Yeah. And so I think I was a little torn because this book is like a good reference for kind of like the steps I want to do. There's also, of course, like the specification itself, as well as OS Dev Wiki pages. But I found that this book just told me like exactly what to do. But I don't really feel good about like pulling up the book on stream and just kind of showing it, because it seems like that's kind of bypassing like copyright in some way. It seems like I shouldn't be like just showing the book straight up. But he does link this source code on GitHub. And here he's got a sample of how to initialize the card and walk the ports and like print information about a device that's plugged into the card. And so that's kind of what I want to do today, is I kind of want to like walk through this, see if we can understand what's going on, and try to get to the point where our operating system can like probe devices and print information about them. And I think that would be a pretty solid point for like a commit that goes to master. Like it's like, that's like a good unit of work, right? Like a implemented UHCI thing that can read device IDs. Wonderful. Yeah, so that's what I want to look at today. And so I think it's probably time to start getting into it. So what's the first thing we want to do? The first thing that we want to do is like initialize the UHCI card, because we didn't really do that last time. So in here, we did get handles to all of the registers we would want to talk to. But we didn't do anything useful with them because we didn't really understand them. And so let's just kind of like walk through what is done here on init, and we can kind of like mimic that to some extent. Okay, so he's got main. He finds the item object on the PCI bus. Great, we don't need to worry about that. We've already done that part. And then here, he is doing some like init stuff, doesn't really matter. Here, he does a global reset. So let's see if we can like pull up some information about what that is. So probably the best thing to do here is to pull up the UHCI spec, which, if I remember correctly, we can find from OS Dev Wiki, but it looks like the OS Dev Wiki might be down. So maybe we do UHCI spec PDF. And this is the one I'm probably looking for. Give it a sec. Hello, refresh, enter. Why? What the fuck? Why is this not working? Here we go. Okay, so here we have this document that is explaining how to work with the USB card. And in here, we can probably see what do these registers do. And we can kind of like cross-check that with what this guy's doing. So what he's doing here is he is writing to the UHCI command register the value 4 and then setting it back to 0 after some reset time. He's doing this 5 times. I think I remembered him mentioning in the book that you have to wait for 50 milliseconds, but he said it's like there's nothing that says it has to be sequential. I don't really know why you would ever not do it all at once, so I'm probably just going to skip this loop. But I am going to do this, like, set the global reset and then turn it off. And we'll see what it says about that in this document. So here we have, like, the USB registers, right? And USB command is the one we want to look at, and he's writing a 4, which is bit 2, which is global reset. So that matches up with what the comment said there. It says, when this bit is set, the host controller sends the global reset signal on the USB, and then where USB is universal serial bus. So it sounds like that's like a bad English saying the USB, but it actually I think is correct because you're saying like I'm sending it on the bus. Then it resets all its logic, including internal hub registers. The hub registers are reset to their power on state. This bit is reset by software after a minimum of 10 milliseconds have elapsed, as specified in Chapter 7 of the specification. So I thought I saw something about 50 milliseconds in here. But no, chip hardware reset flags have the same effect as global reset, except the host controller does not send the global reset on USB. Except it has the same effect as global reset. Oh, I see. Okay. So I guess we can just do what it says here. So I guess here what we're going to do is we're going to make a function. It's going to be an async function because it's going to have to sleep for some amount of time. And we're going to call it reset. It's going to take self by mutable reference probably. And he's going to do that. So let's see. How do I want to handle this? We need to like ask our IO allocator for these like IO ports up front, where IO ports are like, how do I say this? IO ports are, they're like memory addresses essentially, but like on a different bus. And we make this like, we have this allocator for them because we don't want multiple drivers to be interacting with the same IO ports because that could cause like unexpected behavior. So we like make sure that we can only get one of them, so we have to ask for them basically at some point. And probably what we'll do here is we will ask for them when we construct our driver, which means that our IO range will be stored here as a IO range. Wonderful. Perfect. And here, when we construct our UHCI driver, we'll have to take in the IO allocator. Cool. Which means in main, when we construct this guy, we'll have to pass in the IO allocator. Okay. And then what we're going to do is we're going to say, hey, we have this PCI device. So we're going to like find, well, we're going to find the IO range associated with the device. Which means that we're also going to have to pass in the PCI bus stuff. Which means here we have to pass in mute PCI. And then we're going to find what the IO range is for that device. So this is like where we're pulling out some IO ports for this thing. And we had it at the wrong length before, so let's just make sure that we get this right. So this is 12 in hex plus 2, so 14 hex, which is 16 plus 4 is 20. We're pulling in 30, so we'll just do... I think that we can move this back down to 20. And then here we just inject the IO range here. And probably don't need this PCI device anymore. We probably won't need it. Okay. Comment all this up because it doesn't compile anymore. And let's take a look at reset now. So what we're going to do, we were going to set the USB command register. So probably we're going to want like a value to keep track of the USB command offset. So this is offset 0 from the base that we're working with. So they have like a point in memory that we're working with, and this register is like that exact point. And let's see here, what else is we have to do? Then we say IO range self IO range. This is a 2-byte register. So we'll say write U16, write 16 at the USB command offset, and we're going to write the value 0x4. Now, I don't really like doing this like raw write here. What I would prefer to do is I would prefer to convert this command register. Like, I'd like to construct this maybe in some way. So maybe what I want to do here is I want to like take this guy and I want to say struct USB command, and we can kind of like paste these guys in here. And maybe what I do is I convert these into like struct members. And give me one sec. There we go. Maybe I want to make them all lowercase as well. And I need to set their types. So these are all going to be Booleans. These are all single bits. Oopsies. Okay. So now, what am I going to do here? I'm going to say I want to like convert these into a U16. So we'll say impl USB command, and we'll just say like to U16, which takes in self and returns a U16. And then we'll just say what? That the U16 is 0 at first. And we'll say if max packet I guess we just iterate each of these. So we'll say if self max packet ret set bit 7 to true. And we just have to do this for all of these. So I wonder if there's a way to like just automatically do each of them. So we know they're in order. So let's do this. We'll say convert this into a thing that says if self.thing ret set bit 7 true. And then we'll come back and fix the number in them later. Very nice. So this is 7, 6, 5, 4, 3, 2, 1, 0. Wonderful. Easy. Easy peasy. Okay. So now we can just construct this command manually. So we can say let command is equal to USB command. And we'll probably just make all of these guys false. Now, I'm very aware that this is like a really inefficient way of doing this. But it is much easier to parse. And I think that since this is config path, it doesn't really matter. There will be times probably where this is a problem. But maybe not for now. And maybe actually, we might be able to dodge all of this if we just make this a const function. Oh, cannot call non-const function thing. Fuck. I was gonna say that we could just do this all at compile time, but it looks like this like trait thing that we're using to set bits can't be done at compile time, which sucks. Unless, can I write const here? Is that crazy? Functions and traits cannot be declared for const. Yeah, okay. It was worth a shot. Worth a shot. Okay, so this will just be expensive, but fuck it, who cares? And now we can say send command. And it looks like this is failable. Why? Because I might be like going outside of my range, so I'll just assert for now. Invalid offset for USB command. But I'm pretty sure that that'll be fine, because we should allocate the right thing. And then what do? This guy then slept for this time, which is probably just 10 milliseconds. Probably. And then he sets it back to 0. So we'll say reset command, and we'll call this unreset command. There we go. So we'll say sleep, create, sleep for 10 milliseconds. And now we need to pass in this like other shit. So we need to like keep track, find a reference to the time, as well as a reference to the wake up requester, like a way for us to like wake up our executor when the sleep time is up. So probably, I guess we'll just pass them in here. I think it's reasonable to just keep a handle to those forever. That makes like the APIs using these guys easier. So we'll just say monotonic time is this, and wake up requester is this. And we'll just stash these guys here. So we'll say these should actually be reference counted versions of these. Arguably, actually just pass them in when I need them, but I think that this is like nicer for usage later. So time, we'll just stash these in here. So, oops, we copy, we paste, we format, and then we just stash these guys here. Time and wake up requester. Wonderful. And now when we sleep, we can just pass in self.time and self.wakeup requester. And then we wait. Perfect. Perfect. So we'll say let UHCI equals this. And does it make sense for this like constructor to be doing this? Not really. So this should go, because like this construction stuff won't be done in the context where we have async functions available. So probably it makes more sense for there to be like some sort of like initialization stage that does the reset. So what does that look like? Let's think. So he just calls reset. And then he'll do some other stuff after, right? Like all this other initialization shit. I'll have to think about like how this is going to be structured in like construction of the kernel later, because I'm concerned that if this happens too late, then all of a sudden like our other drivers, are we going to have to construct them in like this like second stage? I don't really know. I don't know. Okay, what else do we need to pass into here? We have the time, which is a arc clone monotonic time, as well as the arc clone the wake up requester. So he doesn't like that because wake up requester hasn't been like arced yet. What the heck? This guy isn't even behind a... Ah, this isn't an arc. Sorry, so we'll just clone him like this. And then here, instead of taking in an arc wake up requester, he just takes in a wake up requester. Like this. Cool. What else is it mad at? This function takes 6 arguments if 5 were provided. An argument is missing. So he's got device, IO allocator, PCI, time, wake up requester. Hello? What am I missing? Oh, device, IO allocator, PCI, time, wake up requester. No, I'm missing something. I've got them all. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. What am I... Oh, I have like an angle bracket there that I shouldn't. And that's confusing it. There we go. We need to import the reference counted pointer type. So we just say Alex sync arc, import that guy. And it looks like other than that, we're chilling. I forgot to write the unreset command, so we'll just do that here. Cool. And then in main, we just have to actually call this init somewhere. So I guess for now, we'll just say self.uhci.init. Like this. Okay. Probably we want some debug logging in here too, so we'll just say debug writing reset USB reset. Disabling USB reset. And then we want to enable the debug logs for USB for while we're testing this. So in here, wherever we initialize our logger, here, we can just say, I think it's, we take a slice and we go, string new, the module is kernel UHCI. This is where, and we want the logger to be logger log level debug. And I think that will make our logger work. I think that puts our logger into debug mode, I think. Yeah. Let's see, cargo check. Does look like that compiles. And if I cargo build run release, do we see those debug logs printed? Writing a USB reset, disabling USB reset. Wonderful. Cool. So it looks like that's working. Now, does it make sense to try to like read the registers after that reset just to make sure that everything's in order? Let's do that. So we'll change all these info logs to debug. And we have to change all of these IO range to self.io range. And I think we can just delete this probe function now. Oopsies, that's a lot. I went to the wrong spot. Delete the probe function. And let's see. Oh, he doesn't like that. He does not like that. Why is that? Because our read 16 and write 16 macro or functions are verifying for 4-byte writes instead of 2-byte writes. Oops. Quick fix. Cool. Cool. So these guys all look like they're in reasonable states. And I'm going off memory from last stream. But here, I guess it makes sense to show it. So here, if I just look at the like default values for these guys, we have like USB command register. He's set to 8 because we... Oh, that's interesting. Because we're in global suspend mode. Okay. Status register is showing 20. Okay, so maybe this doesn't look reasonable. These aren't like the default values we expect to see here. Let's see. What does it say here? Time after clearing. Oh, you have to wait after clearing as well. Interesting. So can we look at where this is defined? It's probably in some header file in the USB stuff. Include UHCI is probably... Yeah. All right. So, ready? No, it's not defined in here. USB TRSTRCY. Like, what is this? TDRST. TDRST. Oi. I can't search without being logged into GitHub. That's annoying. I guess I'll just clone this repo. That's probably easier. So here, we'll just go over here and git clone this guy. And where is he? He's in here, and then it was main USB utils. And can I just look for TDRST? Where does this come from? Aha! So 10 and 50. So we just have to wait for another 50 milliseconds, I guess. At the end, it looks like, which we can do over here, somewhere. Where is my window here? So in the UHCI stuff, let's just wait for another 50 milliseconds. Like this. Cargo, run. Let's see if those register values look any different. Why is it just never finishing? What the fuck? What the? There's a bug somewhere in that sleep stuff, for sure. Something about that isn't right. Also, something about this isn't right. The fact that USB command register is being set at all. Oh, I guess because I didn't. I've just made a horrible mistake here. First of all, this unreset command, I didn't change anything. Also, I didn't set the right bit here. What am I doing? All right. There we go. That looks more reasonable. So now if we compare these to the default values that we're supposed to see here, we see like USB command is 000, it's 0. Status register is default 0, but we're seeing a 2. That's interesting. We're seeing a bit 4, 5, 6 being set. Or maybe 5. No, something in there is kind of interesting. But maybe with setting one of the reserve bits. Interrupt regular is 0, like it's supposed to be. FRNum is 0, so I guess we probably have to reset that. As well as the base adder is 0. Soft start of frame is hex 40, great, and our status registers are 80 and 83, which indicate that like one of the ports is plugged in. Cool. So I think we're like chilling there. So let's do the next thing here. Which is, I'm gonna put a fix me here. Sleep 50 milliseconds doesn't seem to work. There is definitely a bug there, and I just don't want to deal with it right now. Okay, so what does he do next? He sets the, does the command register contain its default value? Does the status register, oh, okay, yeah, so this guy's doing those same checks. Yeah, that makes sense. So he's clearing the status register, checking this. I'm gonna skip these checks for now because we validated them manually, and I'm not really too worried about it. If we set bit 1 in the command register after a specified time, the controller should reset it to 0. In my test, the UHCI controller takes less than 2 microseconds to reset the bit. Okay, so here they're doing a host controller reset now, I think. Set bit 1 in the command register. What is bit 1? Bit 1 in the command register is host controller reset. When this bit is set, the host controller module resets internal timers, counters, state machines, etc. to their initial value. Any transaction currently in progress on USB is immediately terminated. This bit is reset by the host controller when the reset process is complete. All right. So we'll just do the same thing. So we'll just say, host reset command is the same here, except we're gonna set true on this guy. And this is host reset command. And we'll say, resetting host, and we'll see for 10 milliseconds again. And we'll see if this guy passes. Oh, wait, did I actually write it? Yep, I sure did. Cool. Cool. And that did reset this, like, some of these other values that we saw change before, which is kind of interesting. Okay, so what's he do next? Next, he sets up this, like, memory address for the frame pointer list. So we've already done that last stream, I think. Let's look. Okay, so this, what are we doing? What is that? Well, first let's find it, and then we'll explain. So here we say frame list is a vector of 1024 with the number 1 in it. So that is this guy here, this list of this like time queue of things to do that are all going to point to a queue. We initialize them with the value of 1 because here that means that for each value we'll set this bit that says this is an invalid frame. So we initialize them all invalid, and then later we'll initialize them with like something else. But we have to put them into the USB card. So once we have this memory, we have like a contiguous area of physical memory. And we can just probably set this guy to that value. So here in the UHCI somewhere, we set the frame list pointer address. This guy, frame list base address register. The 32-bit register contains the beginning address of the frame list in the system memory. HCD loads this register prior to starting the schedule execution by the host controller. When written, only the upper 20 bits are used. The lower 12 bits are written as 0 because it's 4K aligned. Okay. The contents of this register are combined with the frame number counter to enable the host controller. So we actually need this to be 4K aligned. Can I get like a 4K aligned vector in Rust? You can force the alignment of a type. Okay. That's annoying. Vec aligned to 64, where elements are aligned. I just want like the whole vector aligned. How do I allocate aligned memory in Rust? Oh, here we go. Oh, this guy's saying I want this API, but it doesn't exist. By default, Vec guarantees that the memory is properly aligned to the type T. If you want to say allocate an over-aligned slice of bytes, you may find the alloc module of SCD interesting. Yeah, so maybe we do just have to like manually allocate with the layout we want and then convert that into a vector after. Which doesn't seem crazy. I guess we do have like very specific requirements. Right, so here we just ask for a size and alignment. It gives us a layout. And then we just call alloc with that layout and it gives us a pointer. And then we can probably convert that pointer into a vector after. So let's do that. So I guess first, let's just assert that the frame list pointer and Xerox FFF, I think it said, for 12 bits. Yeah, this must be 0. Sorry, so we only want if we look at the bottom 12 bits, we want these to be 0. And I'm pretty sure this will fail right now. So let's just take a quick peek. Cool, so that does not fail. Is this the right number? 4812? Yeah, that is. Oh, oops, and I shouldn't invert that mask. That was a mistake. Yeah, so this is not aligned correctly. And so now what we can do is we can say alloc. What is the like function for this allocator in like non-stud? Standard library. I don't want like this. Oh, here, I want the alloc. Here we go. Alloc. All right. So I call alloc. And we'll say let layout is equal to alloc layout from size align. And we want a size of 1024 times 32, right? For 1024 32-bit ints. So this actually should be times 4 because 32 bits, not 32 bytes. And our alignment is just going to be 1024. No. What's the alignment? 4K 4096. Then we allocate with this layout, which I think just passing the layout. So say frame list is equal to this. It doesn't like this argument for some reason because this can be failed. So we'll just say expect invalid layout. I'm okay with this crashing because we have like hard-coded numbers that should always work. We allocate our frame list and then we convert it into a vector. So we say vec from raw parts. We take in the frame list, the length, which is 1024, and the capacity, which is 1024. And here we have to convert the frame list to a mute U32. So now we should be able to say that we have a vector And also we want to make sure that all elements are initialized. So we'll say for elem in v as a mutable reference. Elem, we'll set the elem to 1, like we wanted before. So now when we run, hopefully we don't hit that assertion that says that we're not aligned correctly. And great, we have like an aligned frame list. Perfect. I guess we could do, instead of doing it this way, we could say that its initial length is 0 and then push them all, but it doesn't really matter. It doesn't matter. This is fine. This is fine. Probably. Probably we should also assert that they're all 1. For elem in frame list, assert that elem is equal to 0 to 1, just to double check. Just to double check. Give it a sec. No assertions, we're good to go. Bing, bang, boom. Okay, so we've got our frame list loaded, and we just have to push it onto the card. So here in our init, we'll say, we make a new IO offset for the frame list, which is at 08. So we'll say, what is this called? Frame list offset is 8 off from the beginning of the beginning of the address range. And then we just tell it that our thing is there. So here we can just say self IO range write 16. Frame list offset. And this isn't a write 16. This should be a write 32, actually, because it's a 32-bit thing. And we'll just write the frame list as pointer. Self frame list as pointer. It doesn't like that for some reason. Does it have to cast this to U32 probably? Nice, and we will expect failed to write frame list offset. Give it a sec. And now we see our thing set to this. And I wonder if that's actually the right number. Let's debug writing frame list offset as this. And then we'll just say self.frame list as pointer. Give it a sec. Nice. Nice. So that's working just like we wanted. So we've now allocated our frame list. We've aligned it to the boundary, like aligned it in the way that the card requires. And now the card is now aware of where we want to go. Sick. What does this guy do next? He sets the address. He sets the size. Oh, this is like his allocation of the thing. Here is him initializing it like we did. And then here he is pushing that thing. And so now he's setting the frame number as well as some of the other state things. So this makes sense. We should do this as well. Initialize it to 0. I guess technically it doesn't matter if we're going to make them all do, like, if it's going to be a cyclical thing, it doesn't actually matter which number it starts at, but starting it at 0 seems like a reasonable good practice. So we'll do that. So we'll say frame number offset is going to be, where does this come from? 6H. And we're just gonna write that to 0 somewhere. Here. And here we'll just go say frame number offset, we're just going to set this to 0. And this is a U16, right? And failed to write frame number offset. And we should see that now. We should see this fr numreg get set to 0 now. Come on. Which we do. Fr numreg 0. Great. And then he does some of these other things. So he sets the frame to 40, which is what we get by default. He disables interrupts, which is also default. And he clears any status bits. That seems pretty reasonable to clear the status. And then what the hell is this? He's enabling bits 7, 6, and 0. So that's... in the command, bit 7 is the max packet size. He's setting to 64 instead of 32. He's setting the configure flag to say, hey, I've configured you. This says this bit has no effect on hardware. It's just flags the system that this is set up. So that's pretty reasonable. And then he sets bit 0 as the run stop bit. Okay. So here we'll say, we need the status offset. Which is what? Which is what? 2. And it's 2 bytes. So we'll say self.io range write 16 USB status offset. I think he wrote 1F to clear it. Yeah. And we'll just comment failed to clear status register. Cool. And then he sets the command. So we'll say, I guess really these things should be in like named functions, I guess. So let's just do that. So this guy is, what's this guy doing? He is set frame list offset. This is not async anymore, so we just say self set frame list offset. This is set frame number, and we'll take in a value here, I guess. So this is a U16. And this just goes to val, and then we say self.set frame number to 0. Pub function clear USB status. And we'll just take this guy, shove him in here. And now that's like a lot nicer to read down below. Wonderful. And so the next thing we're going to do is we're going to say enable USB run, I guess. Enable UHCI card. Maybe this is like the wrong word for it, but that's okay. And we'll just copy this. So the command is he set this to true, and he set configure to true, and run to true. And we can just say here, enabling card. And here we can say command. Wonderful. Looks good, and then we just enable the card. Self.enable UHCI card. And so probably now, if we were to like poll every once in a while, we should probably see this frame number register increment like around once per millisecond. So we can probably prove to ourselves that that's working, because like what's happening here is it's supposed to be iterating this frame list over and over again, and at like 1 entry per millisecond after we enable it. So it would be interesting to see if we could prove that. So what we could do here is we could do for I in 0 to 10. We could like print all this stuff, and then we could sleep for some period of time. 10 milliseconds seems reasonable, and then we could check it again. And we should see the frame number increase as we iterate through the entries. Oh, which is sick. We are seeing that, right? We're seeing this frame number register change as we print. Cool, cool, cool. That's sick. So now our card's like on, and it's like iterating that list of transactions. But every transaction is empty. And so now if we want to start actually like interacting with our USB ports, we need to like insert some USB commands to run in that queue. So let's say that we're kind of done that, and say we're going to start on probing or enumerating USB ports. And maybe we'll also like throw a little git commit in there. And we'll say checkpoint, USB card initialized, kinda. I think from this point on, we probably don't have to set any like registers on the card again, which is pretty cool. Okay. So what's he do here? He just looks at one specific port. He's assuming the port is 0x10. He does move on to next port. So he starts at the offset of the port status. So here we have these like port status registers. And I think that the USB card could technically have more than 2 ports. And I think that you're just supposed to like enumerate until you find whichever ports you wanted. Or until you hit something that doesn't exist. They probably have like a terminator one. I'm going to skip that for now and just assume that we only have 2 ports. And in fact, in this case, we kind of know which port we're plugged into, so we might even skip enumerating ports and might only look we might only look at the port we know about. Just to like simplify the code here. I know that that's like less correct, but we know that our QEMU is plugging in something at this specific address, so we can kind of figure that out. While UHCI port pres. And he says, if we reset the port. I see. So let's see what these guys do. So the port presence. He reads the port and he checks. He does like an attempted check of it. By like doing a write and read, and if we get the value that we expect back, then like that port is there. Otherwise, we're like writing to some random fucking IO memory. So that's kind of weird. We'll just assume there's 2 for now because we know that's true in this case. And I think that there's 2 mandatory ones. Let's see what this UHCI port reset does. So he resets the port holding the bit for at least 50 milliseconds on the root hub. So, okay. Then he clears the reset bit. Do not clear the CSC bit while we clear the reset. The controller needs to have it cleared while not in reset. Also write 0 to the enable bit. Okay. So I guess what makes sense here is we should look at the definition of the port status. And try to like figure out exactly what he's doing here. Which we can get from this guy. So here, we're going to look at the port status / control registers, and that's these guys. And we'll just say struct USB port status, like this. And we'll just like paste this in. And I guess for each of these, we delete the bits, we go to the end of the word, and then we delete everything after. Oops. This doesn't work for multi-word things. Fuck. So let's do it this way instead, where we just manually delete the end of lines because we don't really know where they are. Okay. And then we replace all spaces with underscores. And then we set them to lowercase. We indent them. And we set their types. So none of these reserved ones. And I think are all like... do we have any multi-bit ones? Line status is multi-bit, but everything else is not. So line status is U8, but everything else is bool. Okay. Okay. And then we can just make a 2U16 again. Do I actually want to do it this way? Maybe it makes more sense because we're going to be reading it as well. Instead of like making this like definition like this, we could instead have this just be a U16. And we could make all of these like functions that are setters and getters on it. So let's try that. I kind of like that a little better. So we cut this out, put it here. Oopsies. And for each of these guys, we say this is now a function that takes in self and returns a bool. Which is unimplemented. And then for each of these guys, we're going to need to make a setter as well. So how do we do that? We say record a macro that copy pastes this function, and then prefixes it with set and makes it mutable. Wow, I love it when things just kind of work. And now we just have to stub all these guys out, which is more annoying, but doable. So suspend is 12. So we just get the 12th bit. This setter needs to take in a value. We say self.0 set bit 12 to value. And he doesn't return shit. And we just have to do these for all of them. So reset is 9. Low speed is 8. Resume detected is 6. Line status is 4 and 5. And port enable changes 3. Port enabled is 2. Connected changes 1. And connected is 0. Okay, now we just have to copy paste all of these to their setters. So we say, we record a macro, we copy, we paste, we say this get turns into a set of value. Val is a bool. And we don't return anything. which worked shockingly well. I actually didn't expect that to work so well. So the only problem one is the line status one, which is a takes in a U8, and you should self.assert that val is less than equal to 0, 3. Right, because it only has 2 bits. And there we go. I think we're good to go there on the USB port status. And so what were we trying to do again? We were trying to like iterate the ports and see if there's anything in them. So here we can say how do we want to do this? For port offset in the 2 port offsets, which is 10 and 12. And IO offset is 12. We want to initialize the port in some way. So we'll say self reset port offset. And so this is a async function probably because I think there's going to be sleeps in it. We call him reset port. He takes in himself by mutual reference. And as well as the offset of the port. And what does this guy do? Now we can start like punching this stuff out. So we'll say, we read the port. So we say self dot IO range read. What is he reading? He's reading the port status, which is the U16 at the port offset. We'll say expect failed to read port status. He sets bit 9, which is reset. I see. So we'll say we actually need to convert this into a USB status, port status, sorry. We'll just say val set reset to true. Wonderful. And then we write that back. Cool. And I presume he then waits for some amount of time. So I think we can do that. Look for that guy here. This is a 50 millisecond reset. Which is a sleep for 50. Failed. This is a failed to write port status. And then here we sleep for 50 milliseconds. Then we unreset it. So we clear the reset bit. And we also do all this other shit. Oh, I see. God damn it. So what is this mask? Clear the reset bit. Do not clear the CSC bit while we clear the reset. The controller needs to have it cleared while not in reset. Also write a 0 to the enable bit. Okay. So I guess we read the value again. And he's keeping most of the values here, right? So he's keeping, he's only setting some of these things to 0. What's he setting to 0? We can run. Womp, 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 womp. Give it a sec, give it a sec, give it a sec. So how do we mask this? So the top N bits. So at least the top 4 he's not touching. Where is my like port status? Port status, port status. Here. I guess we do just write this as a binary thing. So we'll say this is format is binary. And he's clearing bits 2, 3, 4. Oh, sorry. Bits 1, 2, 3, 6, and 8, 9. 1, 2, 3, 6, 6, 8, 9. Okay. And everything else he's keeping as is. And so now we can start looking at like, well, what the fuck does that mean? So he's clearing bits 1, connect status change. He's not writing it because it's write clear. 2, he's setting it. He's saying, I want to enable that port. 3, oh no, wait. He's saying he wants to disable it? He's saying disable the port, yeah, because he's writing a 0, right? If I'm reading this correctly. He is masking this, so he's saying clear the reset bit. Oh, because it's write clear, so he's... No, I'm not seeing it. He's like, also write a 0 to the enable bit. Ah, yeah, so he's doing that on purpose. Okay. So he is clear. He's disabling the port. He is preventing a clear of port enable, which makes sense. He's avoiding doing write clears. 6, he is saying no resume for some reason. 8, he is saying it's read only, so there's no point. And 9, he's saying port is not in reset. All right. That seems reasonable. That seems reasonable. So here we'll say val.set. We just have to go back through all of these by name. Connected changed to false. Avoid clearing connection change bit. He is set enable, port enabled to false. That was bit 2. Oh, bit 3, sorry. Port enabled, disable change. Oh, sorry, fuck. So val set port enable changed. He also wants to avoid clearing this. 6 is resume detect. And 8 and 9 is low speed device. And 9 is port reset. Set reset false. All right. And I guess we'll just say that we are referencing this. Okay. Now we write back. So we write 16 bits of the port offset and the value. We'll say failed to write port status. And that is not in the USB spec that we need to delay. If we wait the recommended this amount of time for clearing the reset, the device will not enable when we set the enabled bit below. Okay, that's weird. That's going to be concerning because I think that we don't have like a microsecond capable clock. We can only sleep in increments of 4 milliseconds right now, which is a bit of a problem. But we'll kind of see how this goes, I guess. The CSC bit must be clear before we set the enable bit. So clear the CSC bit, then write the enable bit. So what is CSC? he's saying that he is clearing the... Oh my god. Connect status change bit. And so what's he saying? That it must be set... It must... Do not clear the connect status change bit while we clear the reset. The controller needs to have it cleared and written to while not in reset. Also write a 0 to the enable bit. Okay. So then we just clear it and then we set the enable bit. Okay. So I guess we just try to do a short sleep. And then we do what he says, which is clear. He's not doing a delay in between. He's just clearing them individually. So that's 3. What's he clearing? He's clearing 3 and 5? Val equals the port. He's setting bit 3 and setting bit 5. But why is he ever touching bit 5? That's read only. He must be meaning to do 1 and 3. Oh, sorry. 3 and 5 are not offsets. They're masks. So 3 means 1, 1, and 5 means 1, 0, 1, I think. 0, 1, 2. Oh, 3 is this. And 5 is both of these. Let's see. Yeah, okay. And 3 is 2 bits. But this is read only, so he should never write this. Am I high? Whatever. I guess we'll just assume that that's true. That like this is fine. So we'll just do it our way. We will read. First we read the value. Then we set the clear the port set connected change bit or connected. Fuck. There's so many bits to keep track of. He sets CSC connect status change, which is bit 1. So this is a write clear. So by setting it to true and writing it back, we're saying, don't sweat it. We've seen it. Then he writes the enable bit, which makes sense. That's port enabled. Yeah. Val.set port enabled true. And we write val back again. Woo! All right. And then we wait. Which we are waiting too long in, but that's okay. Then he returns if we see it or something. And 4 is 0. So this is 0, 1, 0, 2, 4. So then he is just saying if it's true, if the port is enabled, then we'll return true, which seems reasonable. So then we say, we read this guy back, and we return val port enabled. Reasonable. So then we can say let enabled is this, and we'll say if not enabled, I guess we'll just log enabled. Debug port with this offset is enabled. And we'll pass in the port offset. Cargo run. let's see if that prints something sane. So we see port with the IO offset of 18 is enabled and IO offset 16 is not enabled. Wonderful, 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 wonderful. So say if it's not enabled, continue. Otherwise, we're gonna have to do some initialization of the port. So what does this guy do? He calls UHCI port reset, and if it's enabled and connected, so we'll throw that in as well to our reset port. So say port enabled and val.port are connected. Yeah. Yeah. And so we'll say if we're enabled and we're connected, we try to get the descriptor. And here's probably where the first piece of like real USB stuff comes in. Which I think is probably a new section. So we'll say at 1:21:30, we are ready to get USB descriptor from device. Yeehaw! Oopsies. We need this open. Okay. Very cool. So what does he do? He issues a setup. Okay, so I think that this is described in the OSDiv wiki on USB. So there's kind of like two protocols here, or two layers. There's kind of like USB and USB host. So this is like talking to the card itself. So this is like making like transaction descriptors, queues, frame lists, etc. But then like in order to talk to a USB device, we send like packets. And these packets are like shoved into transaction descriptors, transaction descriptors, or whatever they're called. And this is like, we need to know like this protocol in order to talk to the device. And so I think somewhere there's a USB device enumeration thing where they talk about like doing a setup followed by a setup followed by a couple other things, and I can't remember where that was. USB device requests, maybe? No. Standard descriptor. I swear I saw somewhere on this page, like you're supposed to do a setup followed by a data read back to back in order to like initialize the device. Maybe under device states. I swear I saw that here. But it is not jumping out at me. Anyways, he is ooh. Yeah, this. Setup stage consists simply of a setup transaction. The data stage is optional. If used, it may contain one or more in transactions. So figure 15 illustrates a setup transaction, which consists of a setup packet, a data 0 packet, and a handshake packet. In this case, an ACK handshake. So presumably that's what we're going to see him do here is he's going to set up the device, then do a couple other things. I think that this might also be related to setting the address of a device. Address. Because if I remember correctly, when we enumerate the ports, if we go through each port and we turn on the port, the device will have a default address of 0. And we have to tell it like, okay, now you go to this address. Otherwise, it will conflict with the next port we enable. So that's probably what he's going to do here. Let's see. So he issues a setup packet, which he just like writes some shit in here. We're going to pretend that we understand this when we don't really. Then probably he copies that into a transaction descriptor. Probably. We're going to have to figure that out. Base plus 4096. So where does this like setup packet get copied in? Here. He copies this to some address 4096. So this is probably just like directly after the frame list in his memory. And it does look like he's just doing manual memory management. Yeah. So the first transaction descriptor that he creates is pointing to the setup packet, which he's copying here. Then he does something called our buff, which he copies into the next segment. Then he copies some queues. And what the fuck is our buff? So for while size is greater than 0 and I is less than 9, what the fuck? He sets up these transaction descriptors pointing to the next 9 packets. What is size here? Size is passed in to this function. Oh, right. So we like limit how much. Okay. So we're like asking like, hey, I'd like to get the descriptor and you will give me back n bytes. And so he's like pre-allocating n bytes of things in like split into multiple transaction descriptors, probably because there's like a maximum size that you can have for each one. And then what's going to happen is probably we're going to issue the setup. Then it's going to copy all, we're going to like issue like a request for him to like give me some data. It's going to the card is going to copy the data that's returned from the USB device into these buffers. I see. And so all that we are doing here is we have our queue of work to do that we give to this like USB controller. And it has a setup packet followed by a buffer. And that's it. And then we pass the address of these transaction descriptors to each other. And then probably each of the transaction descriptors links to the next one. So yeah, here he says the link pointer is linked to the previous thing in the list. I think that's right. Now, where I'm getting a little confused is somebody has to point to TD0. The queue, our initial queue should point to TD0, which maybe it does. This queue vert pointer, which is the element pointer, i.e. the like thing of work to do, or the queue of work to do, he's setting him to 4096 plus 128 plus size of queue head. Okay. That's weird. And who's pointing to TD0 here? TD0 gets put into... He says put the value of TD0 to this memory address, which is 4096 plus 128 plus the size of the queue head. I see. Which is what he initializes the queue to. Dude, this is so confusing. I don't know why you would do it this way. I'm going to do it differently. So, really the thing that we're trying to do here, I think all that's happening here is he's making two, like, we can probably get away with 2 transaction descriptors. We set the size of them in this like thing somewhere, and like we just say, hey, I'm gonna like issue a setup and then ask you to give me some data back. I'm pretty sure that's all that's happening here. We'll double check. And we just have to set the size of the packets to match the size. Yeah, and that's it. And then we'll put this in a queue. Okay, that makes sense. So the first thing that we want to do is our like setup packet. And so what the fuck? The first question becomes like, what the fuck is this? Right? He's just got some like numbers in here. And we're gonna have to go look at the setup packet in the USB OS dev page is probably where I want to do that. And we'll just look for setup. Okay. How are we going to figure this out? So the USB device requests. I guess probably we need to like look at like the anatomy of a USB packet. So each packet will start with a PID field. PID codes are categorized into 4 groups which share the same 2 least significant bits. So setup is 1101. And the first, so it looks like it goes like this. Packet, USB packet. The first thing is PID because this sync field is used by hardware. We don't have to worry about it. And this should be, for a setup, it will be 1101 and then the inverse of that. So if we do 0B1101 to 010, we want to print that in hex. And we see D2. So now we want to see, do we see a D2 anywhere in what this guy's doing? No. So we don't understand something already off rip. Maybe the PID packet is set by the UHCI controller. Because, let's see if I can find this. In our transfer descriptor, we set like the PID in here directly. We set the PID, the device address, endpointer. So I guess like you could argue that like all of that stuff's going to be handled. And the only thing that we're trying to do is set the buffer pointer. So then the question is, what the fuck goes in a setup buffer? So we have the packet identifier, address fields, endpoint field, data field. So address, endpoint, packet identifier. We saw all of those in the transfer descriptor. So we can assume that the card makes those. Then we have the data field, and it can be up to 1024 bytes of data. Cool. So what goes in a setup? What goes in a setup? A token packet indicates the type and direction of the transaction. Depending on the direction of the transaction, either the host or the function send a data packet. The receiving device responds to the handshake packet. Then under packets, a packet was described as atomic unit of data transfer. Packet is an atom, then a transaction would be a molecule. Okay, so the setup stage consists simply of a setup transaction. Where do we find out what a setup is? Like, am I crazy? We have all of these, like, commands that come in a packet, but, like, where's the setup one? Setup packet. Oh, a set address request has the following setup data packet format. Oh, okay. So these, okay. So we're trying to get the descriptor, which has the following setup data packet format. So here we should see a packet that matches this format. So this is 1, 2, 3, 4, 5, 6. Is that correct? The high byte of W value. So this is 1, 2, 3, 4, 5, 6. Does that match what we're seeing in here? 1, 2, 3, 4, 5, 6, 7, 8. Oh, great. 1, 2, 3, 4, 5, 6, 7, 8. So no. No, it does not. Fuck. Oh, wait. Yeah, 8. So this is 8 bits. Oh, here this sets the descriptor length? No. Okay, we'll read this a little bit more carefully. The high order byte of W value specifies the descriptor type. See the table of USB standard descriptor types to the right. Okay. The low order byte of W value is only used for selecting a specific string or configuration descriptor. These should be reset to 0 otherwise. The W index field is only used for string, blah, blah, blah. Different descriptor types have different lengths, which will be discussed soon. Okay. All USB devices must support requests for device configuration and string descriptors, blah, blah, blah. Get descriptor is a valid request for device in the default, address, or configured state. So maybe we can like look at the USB spec. USB revision 2.0 specification revision 3.2. So I guess this is probably what we want. Can we look at this and see if we can find like packets? Physical layer, link layer, protocol layer. This is probably what we want. Packet types, packet formats. Yeah. Data packet. Where is like setup? Or get configuration? Get configuration. Here we go. So this is again P request get configuration. So where is the like how do they like, can someone explain in here what the type, what these like tables are supposed to look like? Oi. If like 1, 2, 3, 4, 5, 6. So yeah, I'm really lost on like why this guy's allocating 8 bytes. 1, 2, 3, 4, 5, 6, 7, 8. But okay, let's see if like the first 6 bytes line up maybe. So where do we see the like values associated with each of these guys? Get configuration here is 8, which just isn't in here. We're not seeing 8. Oh, we're seeing 6. Oh, right, because we're calling get descriptor. Boy. Oh my god. Okay, that makes more sense. 1, 2, 3, 4, 5, 6. Still 6 bytes. But we can at least see if they line up. So get descriptor, he says 0x80. So that matches this. This is like an 8. This is like an 8 for sure. Get descriptor, 6. That's what we saw here is somewhere in this table we saw get descriptor is a 6 here. Then he sets 0001. So what does that show? Descriptor type and descriptor index, 0 or language ID. Refer to section 969. So 1 means string. So he's looking for strings to come out. Okay. Then he sets the length and the descriptor. And then he just has like a couple zeros trailing on the end for some reason. Okay. Sets the size of the packet to return. So that's in here. It looks like, right? He's saying 1, 2, 3, 4, 5, 0, 1, 2, 3, 4, 5, 6. Interesting. So it looks like maybe at the end of the packet, it's expecting a size return. That's kind of weird. But it does seem like otherwise it wouldn't know. I guess like it should be part of the transfer descriptor, I would think, is where we would set our buffer size. which it is. He's putting the size of the buffer in here. Okay. So we set the descriptor. We call it get descriptor, and then I don't know what this extra 00, like this extra size stuff at the end is for. That's kind of confusing to me, but we will maybe assume that it's correct for now and maybe try to find that in the documentation later. But really, otherwise, the setup packet is pretty straightforward. It is like just what we just see there. So I guess we can just make a transaction descriptor for that. Let's try it. Let's try it. So here we can say self get descriptor for port offset. And we'll make a function called async function get descriptor. I'm not sure if it has to be async, but we'll just make it async for now. And we take in the port offset as where we're going to write to. Okay. Maybe we should take the offset by reference. So we'll just do that in a couple places here. No, we actually don't have to because offsets are copyable, I think. Okay. So what are we going to do? We're going to copy this setup packet, but maybe we'll... do we want to like convert it for now into like something readable? Maybe it's fine to just do this for now. So I guess we can say let setup packet is equal to this. So we'll say it's a vector with these bytes in it. And we'll just say that we're copying this from here for now. Probably this guy, permalink. And we are going to shove this guy into a queue followed by some like read requests. So I guess we'll say let setup td is equal to a transfer descriptor. And we'll have to make a transfer descriptor. Maybe his default state is he's going to have nothing set. Okay, what are all of these bits that he's setting? He's setting reply, which is like the status field, and I think that we know that those are like, if I remember correctly, these are all host controller read write, so we kind of skipped setting these the other day. We'll just leave them all as 0, even though he's not. I don't really know why he's not, but we'll skip that for now. Then he's setting 7 shifted left by 21, so he's, Jesus Christ, setting the max len to 7. That makes sense because I think I read in the book that he only wants to get 8 bytes initially, so set max len, we'll set that to 8. Then what else is he doing? What else is he doing? He is then setting if I and 1. Oh, he's setting the data. I see. He's saying this is 7 shifted left by 21. Then he's setting the address, which is 0 in our case, because he's initialized to 0 when he boots. And then he's setting the token setup. What the fuck is token setup? (0x2d). Where does this come from? This is the bottom n bits of the descriptor, which is the PID. Ah, I see. So this is the setup PID. Yes. I get it. So this is setup TD, set PID to 0B, and we'll read the USB spec for this again. Or I guess we know it's 0x2D, and we will comment this as the setup PID. But we actually only have to set to... I think that's right, yeah. I think that's right. Okay. So we have our transfer descriptor. And now we have to put that somewhere. So I guess... And then I guess we also have to set up the transfer descriptor for the rest. Oh, and we need to set the buffer pointer. Oops. So we also have to set this. Setup TD, set link pointer is a link pointer TD. It's going to point to another transfer descriptor. And we don't know what that transfer descriptor is yet. Right, because this is going to be like a queue of things to iterate over. So I guess we actually have to we have to do this in reverse order. So we'll say read transfer descriptor is going to be a 0.8. Eventually we'll put some stuff in there, but for now we won't. And then now we can say that the setup TD set link pointer is the read TD. So a link pointer TD, and we say mute read TD as mute transfer descriptor. Cool. And then we say that we have to set the buffer that we're working with, which is setup TD set data is the setup packet as pointer, as mute pointer. All right. Cool. So now we just need to do the same thing, but with for the read pointers. So what's he do here? He sets the link pointer to be 1 backwards, TD I-1 link pointer. Oh, so he sets all of their link pointers to be the same. So if I thought I understood this as I thought this was supposed to be setup TD should point to buff1, should point to buff2. But he's kind of got them as they're all pointing to the same device, if I'm reading this correctly. Oh, no, because he's adding. Ah, so he's saying that, yeah, okay. So each one is pointing to the next one on the list, but we don't have to worry about that. So, our setup link pointer is pointing to the read pointer, or the read transfer descriptor, and the read transfer descriptor, I think that we can probably get away with a none here. He's not pointing to anyone, because I think we can get away with doing only one read for a small 8-byte thing. We will set the size. Do we have to set the size on all of them? Oh, this is interesting. Let me double check this is right. So here we said 7 is the length here, and he's incremented I've incremented that to 8. And 8 will turn into 7 on disk. Sick. Okay, so here our maximum length is going to be the packet size. Which I think is 8 for his first read, is what he does here somewhere. He says, get descriptor with a size of 8 here, I'm pretty sure. And I think I saw somewhere that there's a reason that he does that. Packet size and size are different? Why would those ever be different? Whatever. He does have them both set to 8 for that one. So let's try that. So our size is 8. And that is the amount of data we want to read back. He has set this to 3 shifted left by 27. The fuck is 3 shifted left by 27? Oh, we don't care about this reply field. We're not looking at it right now. We are looking at this info field. So here he has t minus 1, which is the packet size. Shift left by 21. Sure. So we just set that unconditionally to 8. The address is 0. The PID is token in, so we need to find that, which it means like please read me something. So 0x69. Nice. And so this is in PID. And what else do we have to do here? The data toggle bit is set to 0, so this is supposed to alternate every frame to make sure that we've like set our things up correctly. And we probably have. And then we have to set the buffer pointer. So the link pointer will be nothing. The buffer pointer is going to be the read packet as a mute pointer. So here we'll get the read packet is a 0, 8. So it's 8 zeros, and maybe when we get this back, it'll look a little different. That's the goal. Okay. Okay. Now what? Now what? Let me think. Are we missing anything important here? The link pointer is set. The reply we don't care about. Info. The address is set. The data 0 is set. The size is set, and the PID is set, and the buffer pointer is set. So all of this seems like it's good to go. And so now all we need to do is like create a queue of these things to inject into the frame list. So now we'll say, let queue is queue head, and he's a 0, 2. So the head link, there's 2 iteration directions. The first one we don't really care about, because we have no other queues of work to do. But the vertical one, which is the one which will like auto increment itself, i.e. do the list of things, we want to set that to look at the setup transaction. So we'll say set element link. This is pointing to a transfer descriptor. And that's the mute setup TD as mute transfer descriptor. Great. Cool. So now we have our queue, and I wonder if we just drop our queue into every element in our frame list, if we'll actually see the data if it get set up. So I wonder if we can say, how do I do this? Let me think for a second. So we want to say that the for elem in mute self frame list, the elem is going to be set link pointer at that element to link pointer queue head mute queue as mute queue head. So the idea here is that we iterate over every single element of work that the USB guy might do, and we say in the next time you poll for work to do, no matter what, try to execute this queue. And this queue is our like read transaction. And hopefully if I just wait a little bit here, right, we're gonna like kind of cheat a little bit. I'm gonna like sleep for a full fucking second here. Maybe 2 seconds, because that's enough for it to like iterate over the whole fucking queue. Not that it needs to. What would be nice to see is that our QHeads element link pointer is now set to like, it's been executed and it's now set to none or something. So it would be cool if we could say like q get q element link, and maybe this will be 0. Maybe. So we'll say element link after 2 seconds. Oops, I fucked up my quotes there. And then we probably have to do all of, we need to reset this so that we're not looking at invalid memory. And here we'll just set them all back to none. And I wonder if that will do something. It does look like we're just not running this, so we'll do this. We'll say element link before 2 seconds is that, and element link after is that, and we'll see if we actually get that sleep done. Because I think there's a bug in our sleep implementation where it's not waking up sometimes, which is like kind of fucking annoying. Yeah. So maybe we'll just like, I do see sometimes that if I just like change the number there, we see different behavior, which is just fucked up. But, you know, it is what it is for now. There we go. So element link before 2 seconds is this. Element link after 2 seconds is also that. So that's not good. I was kind of hoping that we would see this guy change to indicate to us that the USB card has like started doing some stuff. But it hasn't. So I wonder, there could be something to do with like a volatile read not happening here. So I wonder how we do that. We look at the element link. We can say read. I wonder if we can say that this is as, take a reference to this guy as a const u32 and read volatile on him. I wonder if that would do it. Right, because maybe the hardware's changed it and like the Rust compiler didn't realize. Maybe. Nope. Still nothing. Okay. What else could we be missing? Maybe we didn't do something else. Oh, he also has a token out at the end, but that's okay. We'll come back for that. He waits for 10 seconds. How else could we test this? Our transaction descriptors are supposed to get a status bit set. It could also be that we just aren't setting some things that we're supposed to set here. So maybe what we'll do is we'll take in these like these guys that I was ignoring and see if setting those changes anything. So we'll say read TD at offset 1 for the status register. That's the same as the reply field. Is equal to 0 or all of this. And I think it's, this is the syntax. Yeah, and we'll just do this for both of these. We'll just see. Maybe that changes the behavior. Maybe not, but we'll see. We do still not see any incrementing of the status, right, of the element pointer. It could also be that when we are setting these elements in the frame list, we need to do volatile writes. That seems quite likely, actually. because the hardware might not see it. So I wonder if we can do that. So we just go dest. For each of these, we say let dest is, or let val, let source is dest read volatile as mute u32, like this. For now. Then on the source, we set these values. And then we write it back. So we say dest as mute 32, mute u32, I should say, write volatile source. Right, because I'm concerned that maybe we're not updating the hardware correctly. Again, we see no progress. Maybe it would be interesting to see if our status registers are flagging any problems. So this guy does say status 0 over and over again. We are seeing that we are iterating over transaction descriptors, or sorry, these like link pointers. And we would think that if we were seeing errors, then there would be a problem there. We would think that we would see errors being flagged in like the status register over here somewhere. Right, like this status, there's all of these guys, these error bits would be set. But we're not seeing that anywhere, right, in our status register reads. It's 0, which means no errors. So why is it not executing our queue? Why not? Let's take a look here. So we do pass in the queue here. It would be interesting to maybe to look at the frame list. So debug, let's look at the self.frame list. Let's see what we get here. These are all set to something. Can we maybe print as hex? I think it's question mark hex, maybe. Oi. Maybe X question mark. There we go. So we do see every element pointing to this guy, and then we should see that the queue head is also at that address. So we should see queue, like, and queue as mute queue head. Hopefully we see that those two addresses line up. Oops, he doesn't like that. It should be as const queue head. Let's check it. Yeah, so we, oh, wait, hold on. That's not good. Oh, it is good, because we're seeing, wait, that's not good. We're seeing 3, which means the terminate bit is set, which is not right. So probably here, when we're going into our set link pointer, our queue head should be setting bit 0 to false. And this should also be setting bit 0 to false. Aha! A little bug there. Wait, that's still wrong though. That's not good. That's still wrong. Let's print out what we're setting. So we're saying setting this value. Let's see it. Let's see it. Let's see it. Oh, I'm an idiot again. This should be false. I don't know why. I was expecting it to be true if I was saying it to false. Oh! Whoa. Element link after 2 seconds, none. That's really good. That's really good. That's really good. Now we just have to make sure that before it's doing the right thing. So we should see element link before and after. Let's go, baby! So here we see element link before 2 seconds is this transaction descriptor, and after 2 seconds it's nothing, which means that like the queue must have fully executed. The hardware did fucking something. Let's go, baby! That's sick. And so now I wonder if we like read the data in our read packet if we see something. So we'll say read descriptor, and we'll print out the data in the read packet. Still all zeros. So that's not good. But we did actually execute the queue. And I wonder, we did forget to do some things here, I think. We did forget to set the setup pack, these last 2 bytes that they set on their version. So we'll just set this to 0800. I think it's probably Little Endian. So this will be 8 bytes. Let's see if we see something different there. Oh, let's go, baby. Let's fucking go. Okay, so we just got data back from the device. And so I wonder if we can actually like see what these 8 bytes are supposed to be and maybe like gather some info about from that. Hell yeah. Okay, so in the USB side, I guess the get descriptor, we should see something come back. So descriptor type, what did we pass in? We passed in 0001. So descriptor type was 0 and descriptor index was 1. So we should see a device come back. How do I know like what the format of this like get descriptor response is? Do I have a thing open here? Standard get descriptor. Descriptors. Here we go. Devices report their attributes using descriptors. A descriptor is a data structure with a defined format. Each descriptor begins with a byte-wide field and indicates a total number of bytes of descriptor. So we got 18 back, I think. Even though we only requested 8. If where would I see that? 18. Then we see 1020008. So let's see what this guy is saying about that. Using descriptors allows concise storage of the attributes of individual configurations because each configuration may reuse descriptors or portions of descriptors from other configurations. Sure. Blah, blah, blah. Where appropriate, descriptors contain references to string descriptors. If descriptor returns a value in its length field that is less than defined by specification. Okay, a device may return a class or vendor-specific descriptors in 2 ways. Device. This is what we asked for. A device descriptor describes general information about a device. It includes information that applies globally to the device and all the device's configurations. A device only has one device descriptor. Here. So we see the length. We see the descriptor type, which is a 1. which says value constant, device descriptor type. So that's what we asked for. We passed in a 1, we got back a 1, I think. Is that correct? Yeah, we got it. We passed in a 1, we got back a 1. Wonderful. USB specification number in binary coded decimal. So we got 0, 2, i.e. 2.1 is 2.1 hex. So that doesn't look right. Device class at offset 4. 0, 1, 2, 3, 4. This field is set to a value between 1 and FEH. Right, so we're starting to look at values that don't look correct to us. Which is a little concerning. Maybe what we'll do is we'll make sure that we're reading volatile from these. So we'll say for I in self dot, or not self, read packet, and we'll say mutable maybe. We'll say we'll say elem here. We'll say elem as mute U8 read volatile. And then hopefully maybe we'll see like a different number come out if we've like forced the compiler to like not reorder stuff around there. We are seeing the same thing, so that's interesting. 102, so we see descriptor type 1, BCD USB is 02, which is just fucking backwards. So I wonder if we've not understood something. It would be interesting to see if I set this like 8-byte thing here. If I say only give me 4 bytes back, I wonder if we'll see a different number come out. If so, then we're like at least confirming something, which we do. That we used to see an 8 here, and now we're only seeing the first 4 bytes come back. I bet you if I set a 3 there, I'm only going to see 1810. Which I do. So there's something about this where, for sure, we're sending it a setup packet, and the device is like retrieving the setup packet and like at least processing it to some extent, only giving us back the how do I say this? Like the amount of bytes that we requested. So we've at least got something going here. With the value that we're seeing in the read back packet is not correct, and it would be really cool to like at least see something there that made me feel like we got the right answer. So I wonder, what is this like ls device field that he was writing over here? So he's doing it based off of the input of something. What is this? So he's reading the status port for the status of a port and looking at the 8th bit. What the fuck does that mean? So here we have the status, port status, bit 8 is low speed. Oh, I see. So if it's low speed. So let's try setting, maybe this is a low speed device and maybe we're fucking up. So let's try looking at that, setting that. So if it's a low speed device, he sets 1 shifted left by 26. So let's try that. And see if that makes a difference. Nope, we're seeing the same data come back. I guess we could make sure that the setup packet is really sending what we were intending on sending. Maybe we could also look at like the transaction descriptor that ran, and maybe it should tell us if it was complete. Or maybe this like ACK packet that we sent at the end is like important, and we have to do that. So this is data out, which is the last thing. Oh, but that shouldn't matter. That shouldn't matter. I'm pretty sure. But maybe it does. I don't know. I don't know. Fuck. Let's make sure that I really am sending what I think I'm sending. So I think I'm sending get descriptor. So this is a type 6. Get descriptor 6. And then I see descriptor type 0, descriptor index 1. Oh, wait, hold on. Descriptor type, descriptor index. So are these backwards? Should this be 1, 0? Let's see, let's see. No, that looks fucked. So why would that be? Descriptor type of 0 must mean something, and descriptor index of 1, let's try looking at this again. So in the spec here, get descriptor. Descriptor type and index. Where are the descriptor types? Descriptors. The device descriptor, num configurations, blah, blah, blah. But how do I know, like, what its descriptor type index is? So it does seem like 0 is not a valid thing to write there. Let me... W value specifies the descriptor type in the high byte refers to table 9.6. Okay, where's table 9.6? Can I just search that? Table 9.6. Ha. So 0 just shouldn't be valid. Oh, but maybe it's a little like a 16-bit little Indian value, in which case having it in that order does make sense. Maybe. Big Indian? Is that? Let's double check what he does. His setup packet is 86010080. Maybe it's Big Indian. Maybe it's Big Indian. If I flip my size field to be the other way around, I still do get that, which is interesting. Huh. I don't really know how to test this further. Okay, I think I'm gonna take a break. Maybe come back tomorrow. I think I'm pretty happy with like seeing some form of progress here. So we didn't really get like a proper USB descriptor like we wanted to, but we sure fucking did like get a lot farther than we started. So at the beginning of the stream, we just had like data structures ready to go. And now we've actually like sent a message out to our mouse and got something back, which involved like initializing the UHCI card, as well as packetizing like a setup request and trying to ask it like, hey, what are you? And yeah, I'm pretty happy with that. That's like, we've also executed like a chain of requests in order to get there. So that's pretty fucking sick. Right? We have like, we queued up like multiple blocks of things and they like sequentially ran through each other. And we got something back, which is pretty fucking cool. I do apologize. I don't think I described things very well as we were going today. But that's because I was too lost in my own thoughts. Hopefully, if I watch this back, I'll see that it's not as bad as I'm remembering. But apologies if it is. yeah, I think that probably I'll come back tomorrow and just try to keep going, try to like actually parse the descriptor, and maybe if we get like really lucky, we'll be able to actually like see some mouse movement or something come out, because what we're trying to do is we're trying to read a USB mouse. So if you liked what you saw, or you want to come back and see what's next, I stream most days at around 1 or 2 p.m. Pacific time, and I stream for like 1 or 2 hours on Twitch. If you're watching on YouTube, there's a link to the Twitch in the description. And if you're watching on Twitch and you want to catch up, but you're not available or don't want to watch live, there will be YouTube videos going up on the YouTube, which is linked in the Twitch description. Yeah, thanks for watching. Catch you in the next one. Bye.